Let's recap a little bit the foundations of how we arrived at geometric deep learning in lecture 1 and in concepts that we perpetuated throughout the following lectures. We have centered our construction of deep learning architecture through the concept of symmetry. And symmetries, as we discussed, are transformations of objects that leave them unchanged. Here we've given an example of symmetries of a triangle. And using models that are invariant or equivariant to those symmetries, we have then constructed the blueprint of geometric deep learning as this stack of equivariant layers followed by nonlinearity functions with some pooling layers in the middle. And finally, if you need predictions over the entire domain, you can add an invariant layer at the very tail end. And using this, as we've seen throughout the course and the deep dives, you can actually rederive and rediscover basically all of the popular deep learning architectures in use today just by choosing an appropriate domain your data lives on and an appropriate symmetry group that your data is equivariant to. And this is just as a pointer in case for whatever reason you haven't seen some of these architectures being defined. This is a pointer on exactly which lecture or which deep dive we have derived each one of these architectures in. So hopefully, through the course of the lectures you've seen so far and the deep dives, you will have convinced yourselves that all of these architectures can be rediscovered using geometric deep learning principles. One architecture that I've left aside is the long short-term memory, for which you can see the geometric deep learning book for a more thorough derivation. Now, we are going to jump into the realm categorical and seeing what lies beyond symmetry groups. So, just to recap one more time, we designed neural networks in a way that's fully resistant to symmetries, either invariant, such that our symmetry on the input does not affect the final output, or equivariant, such that if we apply a symmetry on the input, it will affect the output, but in a predictable manner. And this turned out to be sufficient to derive all the fan-favorite architectures. However, is it enough to just talk about symmetries when talking about what do I want my neural network to be resilient to? Well, to discuss this, let's recall once again what are the axioms for a symmetry group. And this is a slide I've shown you sometime in lecture 1, where you can see all the axioms for a group outlined. And specifically, I want to zone in on two properties. The requirement that your transformations in a group have a unique inverse, and that the set of all operations closes under all the elements. So the first one implies that every single transformation must not lose any information. The second one implies that all pairs of transformations must compose with each other. And actually, when you think about it, you can, in reality, often deal with transformations that are not invertible and often deal with pairs of transformations that cannot directly compose. So if you want to talk about resistance to some operations that might happen in the real world, for example, if you remember the lecture on neural algorithmic reasoning that I gave you last week, we talked about aligning our networks to operations of individual algorithms. But algorithms may randomly create data or randomly remove data. Those are not symmetries, right? So we might want to go beyond what symmetries can explain if we want to go towards a full, true theory of architectures. And it seems to do that, we need a language that's more general than group theory, something that will allow us to talk about structure of generic computation. And as we will discuss in today's block of lectures, category theory offers such a perspective. Now, as we make the transition from the realm of groups and representations into the realm of categories, morphisms, and functors, we will see how a lot of the concepts we have seen in geometric deep learning can naturally generalize into corresponding concepts in the realm of category theory. Critically, they will basically just relax some of the constraints that we had on groups, and this will allow us to build better aligned neural networks, or more precisely aligned neural networks. And one thing to beware if you want to dive into this topic is that many of the introductions on category theory are geared towards mathematicians. So there is a lot of dragons to be faced if you decide to wander out by yourself to investigate this area. So one hope for today's lecture is to also give you a bit of an introductory session that will be more geared towards computer scientists. So here is a rough overview of everything we will do in the next 2 hours. We'll talk a little bit about just philosophical questions. Why should we bother to study category theory, especially for deep learning? Then we will talk about some of the key concepts, categories, objects, morphisms, and functors, which will be necessary to talk about how to generalize geometric deep learning using them. And then we will do a bit of a mini tutorial to get us comfortable manipulating these concepts and also derive the concept of a monad. Once we have rediscovered what a monad is, we can use it to rederive geometric deep learning as monad algebra homomorphisms. This might sound as a mouthful. I promise you it will make sense by the end of the 2 hours. And then, once we've rediscovered all of GDL, we can generalize monads to arbitrary endofunctors and invent equivariance constraints that have nothing to do with symmetry groups. So that should be pretty interesting. And then we'll also talk a little bit about, because geometric deep learning fundamentally talks about semantics. It talks about what are properties that an architecture should satisfy, but it doesn't necessarily tell us how to implement an architecture, which is more in the realm of syntax. We will talk a little bit how we can use this kind of tool to also talk about implementations of architectures. Expect many take-home or on-the-spot exercises, and a lot of what will be covered, especially at the beginning, will be basically foundational category theory material. So I need to apologize up front to those of you who have taken a category theory course. Some of this will be a little bit slow at the beginning, but I hope you will find that it is worth it. So, this is the paper that started it all by Eilenberg and MacLean, General Theory of Natural Equivalences. And one thing that can immediately give you encouragement that this is a good direction to go in if you want to generalize geometric deep learning is just by looking at this quote from their paper, that you can look at category theory as a direct continuation of Felix Klein's Erlangen program. And as we said in the very first lecture, Felix Klein's Erlangen program is the cornerstone of geometric deep learning. So this is really a great place to start from. Okay, so now let's jump into what is a category. Simply put, as a first sort of intuition tool to look at these things, you can think of categories as basically directed graphs. So they consist of a universe of objects. So objects are these nodes over here, A, B, and C. And you also have a collection of morphisms between them, so these arrows connecting different objects together. Now you might be wondering, why am I using the word universe rather than the word set? This is merely so I do not run into paradoxes like Russell's paradox, because in many cases these objects may themselves be sets, and when you start talking about sets of sets, you run into problems. Okay? So there are ways to work around this. We won't talk about this here in detail, but this is the reason why I'm not using the word set. And these objects and arrows are not just randomly placed in space. We need to actually have them obey certain constraints. And you can see the list of those constraints outlined below. First, for every single object, I need to have a unique identity morphism associated with that object. Secondly, whenever I have two morphisms such that the endpoint of the first one matches the start point of the second one, I must be able to compose them. So there must exist another morphism, G circle F, which is the composition of the two morphisms. And also, it must hold that if I compose any morphism with the corresponding identity either at the endpoint or the start point, I will get back the same thing. And also, associativity must hold. So if I have any three compatible morphisms such that the endpoint of the first matches the start point of the second, the endpoint of the second matches the start point of the third, it doesn't matter in what order I do the two compositions, I'll still get the same thing at the end. So as long as all of these things are satisfied, you have a valid category. And typically, we study categorical constructs by using these commutative diagrams, which look a bit like this. And what do we mean by a commutative path in a diagram? We mean that you take two objects, and any pair of paths connecting these two objects are identical transformations. So in this case, what we're saying with this diagram is that G circle F is the same as the direct arrow G circle F. Note that this is more relaxed than a group. We no longer require that all morphisms have an inverse. We still have identities, but there's not a single identity. We have a separate identity for each object. And also, not all pairs of morphisms can compose with each other, unlike in a group where all pairs of transformations can compose with each other. So this concept strictly generalizes a group. And critically, this is maybe the one kind of mental hurdle that I had to overcome when I started to learn this area. We never assume that we know what's inside the objects. This is one thing that's very important about category theory. It looks at the structure of the arrows, the structure of computation. It doesn't necessarily look that much at what's being computed. And this is great because it allows us to focus just on the structure of the computation and not get too bogged down into details. And therefore, it's traditionally been an excellent recipe in mathematics for discovering connections between disparate constructs. Now, just to make sure that we are comfortable with these axioms, I'll give you a few examples of what is not a category. So, all identities must exist. If I do not have IDA, this is not a category. Similarly, all possible compositions must exist. So you have basically a transitive closure of all of your morphisms. So this is also not a category. If there's no arrow from A to C that composes G and F, this is not a valid category. Why am I telling you all of this? I'm telling you all of this is because often I will not draw every single arrow that exists in my category. Often there might be infinitely many of them, right? So I will only focus on the arrows that are important for the point that we need to make. But you should always have in the back of your minds, if I do not draw an identity, it still must be there. It still must exist. It's just not there to not clutter the picture. Okay? Now, let's start studying a standard category, which is one of the first ones you see when you approach this topic from a computer science perspective. That is the category of sets, also known as just set. So how do we define a set category? Individual objects in that category are sets, and morphisms are functions. So functions from one set to another. Here you have one particular example of a set A and a set B, and a particular morphism which maps elements of A to elements of B. Now, of course, as I said before, you should never ever think about the category as giving you these things directly. Rather, all you see is this. You see an A, you see a B, and you see an F connecting them. You do not see what's inside A, you do not see what's inside B, you do not see how does F map different elements of A to different elements of B, right? So the category is oblivious to what's inside the sets. By the way, it's a good exercise to make sure you understand the axioms, that if you can show that set satisfies all of the axioms of categories that I showed you on the previous slide. Now you might be wondering, if we are forgetting entirely what's inside the two sets and what the function is doing, does this not drop a lot of data? Does this not make it a bit weird to work with? Well, I would say the answer is not quite. You can learn a lot about objects by studying how they interact with other objects. And I will actually show you a result that might be quite simple when you think about it in retrospect, but when I first discovered it, it was pretty mind-blowing. So let me show you how you can rebuild everything inside A and B without ever looking inside A and B. So first, let's discuss a special set which has only a single element, right? In functional programming languages, you might often see this set denoted by open and close parentheses or just unit. And what can you tell me about morphisms from any set A to unit? So what do the morphisms from A to unit look like? How many are there? Yes, there is exactly one morphism mapping any set A to unit. And this actually uniquely defines unit up to isomorphism. There is infinitely many single element sets. But if your set has this particular structure, you can identify it just by looking at patterns. And this actually uniquely identifies the unit set. You only need to look at the structure of the morphisms and not look at the sets themselves. In category theory, an object that has this property is also known as a terminal object. And one thing that's interesting is you can also define a converse notion of an initial object, which has exactly one morphism coming out of it. So only one function coming out of it in the case of sets. So what would the initial object be for sets? Any ideas? Yes? Exactly. So the empty set is the only set such that you have exactly one function coming out of it to every other set. That morphism is sometimes called absurd. It's like the function of give me nothing and I will give you something, right? There is exactly one function from empty set to any other set. That's the empty function. Now, once I have this structure over here, and we basically have identified the unit by looking at patterns inside the arrows, now let's see what comes out of unit. So what can you tell me about morphisms from unit to any particular set B? How many morphisms will there be, and what will they tell you about B? Yes? Yes, exactly. So there will be exactly one morphism per element of B. I've numbered them here just to make the notation consistent. And they are also, that's the reason why they're sometimes known as constant functions. This is particularly useful in functional programming where everything is a function. So constants can be interpreted as functions from unit to the set of inputs of your particular type. And this is it. In some sense, you can uniquely identify every single element of a set just by the morphisms that come out of unit and connect it to that element. So even though we only looked at morphisms, I was still able to reconstruct any set I want up to isomorphism. So just looking at arrows is still very, very powerful and still tells you a whole lot about the structure of these objects. So in summary, category theory allows us to detect patterns in computation, or basically patterns in the morphisms, without looking at specifics of what's the data that we're computing over. And this is all done without really drastically losing information. Like you can still reconstruct what was inside every single one of these sets. And as a result, category theory is arguably perfect for our purposes, and generally, as I said, a wonderful tool to connect disparate areas of math. Now, before we go further, like what I'm going to do next is I'm going to show you some categories other than sets that we're going to find useful for our discourse today. But before we do that, I need to give an important disclaimer. Like I've shown you some results about the set category, like what's the initial object, what's the terminal object, things like that. All of these results are under the assumption of what's the category you're working in, and that's very important. So whenever you want to make a category theoretic argument, you need to first establish what is the category you're working in, because results from one category do not necessarily transfer to another. Here is a very simple example of category rel of relations. So the objects of rel are the same as objects of set. They are the sets. But morphisms are now not functions, but relations. Can anybody tell me what would be the initial and terminal objects if my morphisms are now relations? So which sets have exactly one relation coming into them and one relation coming out of them? Yes? Exactly. So you can convince yourself that inside the category of relation, both the initial and the terminal object is the same, the empty set. There is exactly one relation coming into the empty set. There is exactly one relation coming out of the empty set. Okay. So, because we're going to be talking about neural networks, we need to talk about vectors and how these vectors transform. As a result, we need to use a category that allows us to reason about vector transformations. And the standard option that is often used when resolving constraints on vector computations is to use the category of vector spaces, vect. Now, objects in vect are just vector spaces V. So if you have forgotten what vector spaces are, they are just sets of vectors. So these are still sets, by the way. This will be a subset of set. But the objects are now sets of vectors that have support for the standard vector operations like addition, scalar multiplication, and the usual axioms about vectors that need to apply. What are morphisms in vect? They are just linear functions mapping one vector space to another. So if these were finite vector spaces, you can think of these morphisms as matrix multiplications, right? And therefore, if you look at finite vector spaces, the study of finite vector spaces is exactly the study of linear algebra, which is great because this is where deep learning lives. Now, let's talk about groups. The object that we looked at time and time again in this course. How do groups look like as categories? So let's think about all of the constraints of groups that we dropped while transitioning from groups to categories. If you remember, groups have exactly one identity, so we need to make somehow all of these identity morphisms exactly the same. And we need to make all pairs of morphisms composable to satisfy closure. And we also need to make all morphisms have an inverse. Now, maybe you can see that from these two properties alone, like making all identities equal and making all pairs of morphisms composable, you can already tell me something about the set of objects for a group category. So what can you tell me about objects in a group category? How many objects there are going to be? Yes, exactly one. Because, remember, I told you there needs to be a separate identity for every object. The only way to have all identities the same is to have exactly one object. There's no other way to do that. And actually, the same property allows all pairs of morphisms to compose, because if all morphisms are object to object, then their composition must always exist, right? So the first two conditions actually resolve to exactly the same shape. And we often denote this category using the notation BG, and G is its sole object. So this ensures we'll have exactly one identity, and all morphisms from G to G will be compatible to compose. Now, about making all morphisms have an inverse, we need an extra condition that every single one of these morphisms must also have a unique morphism going the other way. Or in category theoretic terms, you need to have all of your morphisms be isomorphisms. And what does this mean? This means that for every morphism, there must exist a morphism going in the opposite direction, such that if you compose, you get the appropriate identity. Well, in the case of groups, there's exactly one object, so these two will actually resolve to the same identity. And you can then treat this G morphism as the so-called inverse of F, and sometimes denote it as F to the minus 1. So if you can ensure that these morphisms always exist, now you suddenly have a group. So a group is a single object category where every morphism is an isomorphism. Now, clearly, this is a super special case of what category theory has to offer. But if you'd like to play around a bit more with manipulating morphisms of single object group categories, you can try to prove that the inverse of a composition is the same as the reversed composition of inverses, using only the definitions I've given you so far. Okay, now what happens if you just have a single object category but omit the requirement that all morphisms must have inverses? You actually end up with another generalization of groups, which are known as monoids. You might have seen monoids if you've studied abstract math before. So here, your operations in a monoid no longer need to have inverses, but they must all compose. And this is actually a very popular construct for dealing with repeated algorithmic computation, because steps of an algorithm must always, if it's kind of one automaton, they must always compose with each other. But sometimes an algorithm might make irreversible steps, and you won't be able to revert what you have done. So this kind of monoid structure we often denote as a BM category, and its object is just M. And by the way, if you were wondering why these things are called monoids, this is the reason why. Monoid as one object, right? This is the reason why monoids have the name that they have. And just as a remark, you can also omit the second property of groups rather than the first one, so you can still have all morphisms having inverses, so all morphisms being isomorphisms, but instead not making all morphisms composable with each other. This lands you with the concept of a groupoid. So this is something that kind of looks like a group, but it's really just a collection of these equivalence classes where every pair of objects must be connected to each other with an isomorphism in individual islands. Okay. So we've talked about a few special cases of categories. We looked at set, we looked at rel, we looked at groups, and we looked at monoids. But really, the power of category theory starts to emerge when you let multiple categories interact with each other. And just like you can define functions between sets, you can define functors between categories. Now, remember, categories comprise both objects and morphisms, so the functors must map both objects of one category and morphisms of that category to objects and morphisms in another. So, generally speaking, if we let C and D be categories, we can define a functor, capital F, mapping C to D, such that you have f of x for all objects x in C, and f of f for all morphisms f in C, mapping them to corresponding ones in D. But this cannot be done arbitrarily. A functor, to be a proper construct, must respect the structure and compositionality inside C. So what this means is that it must satisfy these two constraints. If I choose to transform the identity arrow of a particular object, that must transform to the identity arrow of where the object lands in the other category. That's the first constraint the functor must satisfy. The second one is if I apply my functor to a composition of morphisms, I should get the same result as if I first applied the functor to the two morphisms separately and then composed the result. As long as these two properties hold, we have a valid functor. And one very typical concept that we will use a lot today is a functor that maps a category to itself, which we often call an endofunctor. Now, once again, this is maybe best visualized in a picture. So here is the previous commutative diagram I've showed you of a category with 3 objects and 2 morphisms in a composition. Now, what would a functor do? A functor would then map every single object and morphism of this category to corresponding objects and morphisms in a different category, such that this nice triangular structure is respected between those objects. So whenever you have this commutative structure in the original category, it must be preserved in the mapped category. Of course, just to be clear, you can also satisfy this triangle constraint by just mapping A, B, and C to exactly the same object. This is totally valid, and will often emerge when you have functors out of groups, for example, single object categories. However, the equations must be satisfied in either case. So these objects need not be distinct, f of A, f of B, and f of C, but the rules combining them must hold. And perhaps one other good way of talking about functors is that they generalize the concept of analogies. As this great quote from John Bayes says, every sufficiently good analogy is yearning to become a functor. Okay. Now, much like you can have functors as a concept that connects 2 categories, you can also define a concept that connects 2 functors to each other, and this is what's known as a natural transformation. It's one of the most powerful concepts in category theory, and in fact, Eilenberg and MacLean, in their original paper, invented functors in order to define natural transformations. So how does it work? Let's imagine I have 2 functors, f and g. They are both compatible, so they're mapping between the same 2 categories. And a natural transformation alpha connects the 2 functors, so it maps f to g, as follows. For every single object x in my first category, the natural transformation defines a morphism in the other category, which connects the 2 mappings of that object, in such a way that this compositionality constraint is satisfied for every single morphism connecting x and y. So how does this work in practice? This is best visualized once again in a diagram. So imagine I have x and y in my original category and the morphism connecting them. And now I have these 2 functors f and g, which map x and y into 2 different places, and obviously also this morphism into 2 different arrows. So the natural transformation is this collection of blue arrows for every single object that allows me to close this square. And this square then must commute. This is the idea of a natural transformation. It's not a single morphism, it's a collection of morphisms, one for every single object in my initial category. And one way in which you can call these individual morphisms are the component of the natural transformation inside X. And often, we won't have to draw all of these individual arrows and functor mappings. We can just draw the naturality square, and that should be enough to explain what we want. But I've kind of explicitly drawn all the variables here just so you can see how they relate to each other. We are relating functors f and g by this arrow that crosses from one to the other. Okay, so this was our initial tour through the key categorical concepts. This is just to recap, whenever you talk about these individual objects, what do you need to specify in order to talk about them? So to specify a category, what do you need to tell me? You need to tell me what are the objects and what are the morphisms. And if it's not directly trivial from your definition of morphism, you need to also tell me how they compose and what the identities are. If you want to specify a functor, you must describe the 2 categories you're connecting, the mapping of objects from one category to another, and the mapping of morphisms from one category to another. And if you want to specify a natural transformation, you need to specify the 2 categories that are being related by the 2 functors. You need to specify the 2 functors that the transformation is relating. And then in every single object in the first category, you need to specify what are the component morphisms in the second category that connect the 2 functors. Okay. Now, in order to be able to talk about geometric deep learning models, we need to be able to talk about group actions. That, if you remember, through the concept of group action, we rediscovered equivariance constraints, and then all of the stuff we did in subsequent lectures was really just an extension of that one rule, right? So group actions are a critical thing for us to reason about. And we can also make a category theoretical version of a group action. by using a special kind of endofunctor known as a monad. I hope that a fair amount of you have already heard what a monad is. You might not necessarily exactly know what it is, but I hope you've heard about the concept. It's a very universal but somewhat tricky mechanism of expressing contained computation functional programming. For those of you who have done some Haskell, you might recall definitions like these. For those of you who have went on troll mathematics stack exchange websites, you might have seen a monad is just a monad in the category of endofunctors. I don't see what is the problem. And as a result, the number of tutorials for what a monad is has been skyrocketing in the past 30 years. People are really trying to explain this concept in a way that makes sense. Hopefully, I will not add to the noise and help you a little bit there. Okay, so what is a monad categorically? So first of all, we define a monad inside a category C, and we define it as a tuple of three things: M, eta, and mu. The M is just some endofunctor, so some functor mapping the objects and morphisms of C to itself. And we have two special natural transformations, which are sometimes in functional programming known as return and join. The first one connects the identity endofunctor, which just is the boring endofunctor that maps all objects to themselves and all morphisms to themselves, to our particular target endofunctor M. And a natural transformation join, which maps the composition of two functors, of the endofunctor with itself, to just the endofunctor. And functor composition works the same way as morphism composition works. You can just compose the mappings from one to the other. Okay, one way in which you can interpret these components is M is like a container which specifies some computation that you want to carry out. And the eta, so eta and mu, remember, they're natural transformations. So we define them in every single object of our category. So eta of x is now a morphism from x to m of x, which basically allows you to create a new container for every single x in your category. And mu looks at a stack of two computations and flattens it into just one computation. So it's a way to like perform one level of nested computation. Right? And now for this to be a monad, it must satisfy certain axioms. And specifically, these two diagrams need to be satisfied. They need to commute. So let's just try to interpret them. If you have an object which is contained inside the endofunctor, and you use the first natural transformation to wrap another layer of computation around it, note that this eta is supposed to be more like an identity wrapper. It doesn't really change the object, it just wraps it into M. If you then take this nested computation and you resolve it using mu, you should end up with exactly the same thing you started from. So these two need to be equal, right? And the second axiom that must hold is that if I have a 3-deep nesting of computation, I can either decide to first join the first two and then join the result with the third one, or I can choose to join the second two and then join the result, so associativity basically in how you're applying this join operation. Now, just to kind of ground this in a particular standard example, one typical monad that you might encounter as one of the first examples is the power set monad. So we call this endofunctor P, and it's applied on sets, so P maps set to set. And specifically what it does is it maps individual sets to their power sets, right? So the sets of all of their subsets, which are themselves sets. So P of x is also a member of set, right? And it maps individual functions from x to y, which are the morphisms in set, to functions between their power sets. So P of f will be now a mapping between P of x and P of y by just applying f to each relevant subset that you have in your collection. Now, what about eta and mu? Well, eta, as we said, it's just supposed to take the object as it is and represent it using the computation without doing any changes on it. So eta of x just converts a set into its power set representation. It doesn't do anything else, right? Whereas mu will take a power set of power sets and reduce it to just a single power set by performing a big union over all of the things inside it, right? Now, once we have this idea of a monad, we can finally talk about what are group actions as monads. And once again, we will be doing this on the set category. Formally, the group action monad is this particular endofunctor, G times blank. And we'll talk about what that is in a second. So G times blank is, as we said, an endofunctor from set to set, which maps individual sets X to products G times X, and functions that map one set to another to just functions that map products by basically ignoring the G element and just applying F on the second part, right? So hopefully it makes sense why this is an endofunctor. What this does is it takes any particular set you might want your group to act on, and it attaches the set of all possible group transformations together to it, so you can act on it, right? And now what are then the two transformations, right? We need to have the return, the eta, which will take any particular set and just not transform it, but make it look like what the monad expects. In this case, as you might expect, it is attaching the identity group element to it, right? So eta is just giving us a component function that maps every single set X to just EX. So E is the identity group transformation. And mu, as you might expect, as you remember, it looks at the composition of two M's. So this will now be G times blank. And it reduces it to just a single G. As you might expect, we have this now triple product of group element G, group element H, and some element X. All it does really is compute the composition of the two group operations and sticks it as the thing to transform X. So hopefully you can convince yourselves that this is a valid monad, and it is a monad that will actively track all the group actions you are performing on a particular object that you want to transform. So one thing which is important to note here is that monads will tell you how individual group actions compose, but they do not let you execute those group actions. So at the end, we're still left with this GHX, but we haven't told you how will X change as a result of doing that application. To do this, we will need some more machinery, which we will cover in the second lecture. So we are going to stop here for now, take a 10-minute break. If you have any questions, please do come over and ask. And yeah, hopefully this has been an interesting introduction to category theoretic concepts. In the second lecture, we will learn how to execute these things, then learn how to rediscover all of GDL using it, and then how to go beyond GDL. Thank you. And please have some more chocolate.